available right outside this room for your discussion and so on. So let me introduce first presenter. First talk is titled How to Break Crowd Simulation Algorithms by Alexander Chan from the Academy of Math, Science, and Engineering, and Tomo Weiss, assistant professor in the College of Computing at the New Jersey Institute of Technology. And by the way, I'm Taro Narahara. I'm a session chair today from NJIT, New Jersey Institute of Technology. So let me just quickly introduce the speaker today, Tomo Weiss. He is assistant professor from NJIT, and he received his PhD in computer science from UCLA, working with Professor Dimitri Terzopoulos. For his PhD work, he was a finalist in both ACM SIGGRAPH Thesis First Award and the ACM SIGGRAPH Asia Doctoral Symposium. He received multiple awards, including the Best Presentation Student and Paper Awards for his work on crowds and collective dynamics simulations in graphics conferences, including motion in games, i3D, and the Symposium of Computer Animation. So please welcome Tomo Weiss.
Thank you. So thank you for that nice introduction. I'm gonna, this is myself, and I think we have enough crowd today for the talk about crowds. So I'm gonna talk about virtual crowds. So first of all, what are crowds? So crowds are something you may or may not encounter when you're going on a commute to work, or something you may see when you just walk on the city street. So those are the real crowds we kind of engage with every day. Virtual crowds are a little bit different. So first of all, when you're creating virtual crowds, you need to actually model them. Then you need to add some sort of animation so they look kind of interesting and realistic. And then you can kind of bring that all together into some sort of nice scene when you're Houdini, Blender, or whatever framework you're using. So there's multiple layers on when you're creating virtual crowds, be it rendering, animating their motions, altering the scenes, which is basically the act of actually placing the crowds in a scene and telling them what they should be going about doing, and also on simulating crowds, which is basically controlling the mechanics of how they move about in a scene in a way that kind of seems realistic. So I'm going to talk about the simulation aspect right now. So I want to differentiate between animation and simulation. So animation is what you see here on the left is basically how the character walks, how their head moves, how their hands sway, and all of those kind of aspects. So I'm going to just focus on simulation for now. So that basically focus on the very primitive motion of the agents, kind of in a space, assuming the agents are particles or disks or spheres or something like that. So there are many crowd simulation algorithms. Most of them are divided to macroscopic or continuum-based algorithms that are kind of more based on looking at a crowd as a material. And there's also individual-based algorithms which are kind of focused on modeling specific agents. And that's where I'm going to focus on here. So summary so far, if you just entered and you want to know what's going on. We're talking about virtual crowds, and under virtual crowds, we're going to talk about crowd simulation. And in crowd simulation, we're going to talk about microscopic algorithms. And in these algorithms, we're going to only talk about 4 algorithms, which are kind of recurring in many frameworks. Again, what do these algorithms do? So you have a collection of these agents, usually disks, and they move about a space, and each agent has their own kind of velocity, acceleration, position, and so on. So these are the algorithms that we're going to test in this talk, and I'm going to talk about them in a second. But the common theme here is that they all focus on kind of short-term behavior, so there's no path planning or kind of high-level kind of consideration on their movement. They're just trying to avoid collisions while going towards their goal. And also another common theme is they're all kind of behaving like particles, so they have a force that controls their motion. The force changes their velocity, and based on that velocity, they change their position. And we assume typically all agents are disk-shaped, And so they only use geometry, positions, and velocity to move about the space. So the algorithms here are something that you'll probably see in many of these frameworks. So for example, social force is kind of super well known. And we have it or either as is or as a plugin available in Houdini, Maya, Blender, and Unity, and so on. So these other two algorithms, which are called PAM and TTC in short, are very frequently compared in state-of-the-art crowd simulation work. So you can see a lot of comparisons with them if you're reading these papers on crowds. And this latest one, the MS paper, is kind of a multi-choice augmented social force approach. So once you have one of these algorithms, you implement them, you usually get something that looks like this, and that kind of means that it's working. But what I want to show today in the talk is there are some deficiencies in these algorithms, and I'm going to see how basic tests can kind of handle them and show these deficiencies. So these are our test cases. So our first test case is basically two agents just kind of heading straight towards each other. So what you want to see is kind of this collision avoidance behavior. So they're not going to touch each other. They're just going to pass by each other. These two tests are kind of similar. So you have one slower agent and another faster agent trying to overtake it. And this is the sort of behavior you would want to see if you have a successful implementation of the algorithm. And then the final test here is also kind of very simple. We just have two agents trying to cross each other's path. Again, there's no path planning here. There's very simple, straightforward kind of motion and collision avoidance behavior. So again, the common theme here is they're simple. You often run these test cases when you're implementing them in code or when you're trying out a new algorithm or whatever, just to want to see if it works. And we are going to demonstrate how they actually fail in these kind of works. So let's look at the results here. So in this kind of orthogonal crossing scenario, you can see the common used algorithms, TTC, PAM, social force are kind of, yeah, I know. They kind of fail, and they're not really doing well. While MS does actually avoid that collision, which is kind of nice. Here's another test case with overtaking. So a slower agent is kind of walking there, and the faster agent tries to overtake it. But as you can see, this kind of fails again in these cases, except for the MS case. So that one is wood. So the stationary cases where like there's like one agent that's like just standing there, and it's very similar to overtake, like they're just not able to move around in like TTC, PAM, and social force cases, but in MS, he does manage to go around that agent. And final algorithm here is oncoming, where basically they're just head-on, kind of trying to avoid colliding with each other. And as you can see here, they're also going to not do too well, but in MS, they kind of. So this is not an advertisement for MS, but I'm just going to talk about why it actually succeeds in a second. So as you just saw these algorithms, the SF, PAM, TTC mostly fail on very simple benchmarks. Doesn't mean they're not good. I'm going to explain why, but they just fail, and this is because of there's like some sort of the force they compute are not the right forces. So here's an illustration. So imagine you have these two agents kind of trying to pass each other, right? So this is basically the velocity vector, and they kind of lie on the same vector between their disk centers. So the force will just kind of act opposite, kind of directly opposite to that. So that's what's going to cause this stalemate. So this also appears again in different kind of configurations, geometry-wise. So the MS algorithm passes because there's some sort of randomness in its behavior. So basically, instead of just deterministically doing the opposite force, it actually chooses between a couple of options, and it kind of selects the best one between them. So, so one way to avoid this is to use other algorithms, but to be less funny, you can actually augment algorithms if you have access to the code. You can add all sorts of correctional forces that can kind of move the agents away from colliding if that will happen. But if you don't have access to the code, you can just augment the setting that you are simulating. So you can vary the positions of the goals and so on of the agents, the number of agents. So for example, here's the same kind of unstable case as before. So what you can do is you can only so slightly move them away from that center line. And that basically mostly solves the issue. So here you can see we have PAM and TTC with that kind of slight augmentation. So they're no longer like exactly on that same line. And PAM is basically still not so good, but TTC does actually pretty quickly use that and resolve the collision. Okay, so how does this generalize? So basically, if you're using any of these domains, gaming, robotics, or even if you're simulating animals or insects, you have some sort of collision avoidance algorithms that you're using for either like physics simulations or for just general VFX. And you may or may not use these same algorithms, and you may not even know it. So you may want to just pay attention and kind of try to see if there's small augmentations that can help you kind of just make your crowds look a bit better. Also, by the way, just advertising, we have a poster on insect simulation here in SIGGRAPH. So for future work, we're going to actually look at how to extend this to larger crowds, so not just on these simple test cases, kind of finding like what basically is a failure when you're doing crowd simulation, how do you define that failure? We're also going to craft additional test cases. They're not just those simple geometries that you saw. And we're also going to check robustness to noise and other variations in future work. So to summarize, what we saw in this talk so far, we saw straightforward case scenarios where existing models fail. We discussed some solutions, and I hope this inspires future discussions for some sort of systematic evaluation of multi-agent algorithms. And that was my talk so far. Thank you.
So we have enough time for several questions. There's microphones over there, so please move to the microphone if you have any questions. This one.